When working with spherical coordinates, we want to think of space as a giant sphere. When we have a point in 3 dimensions, we can describe it using x, y, and z as we're used to, or we can describe it using rho, theta, and phi. Rho is the Greek letter r. It stands for radius. It is a 3-dimensional radius coming from the origin out to the point. Theta is the same theta that we know from polar coordinates and just from working with angles. Theta is measured from the positive x-axis moving toward the positive y-axis, the angle coming around that way. Phi, or phi, is another angle. This angle is measured from the positive z-axis going down. So we have 2 angles, theta and phi, and 1 distance, rho. Unlike cylindrical coordinates, which has 2 distances, r and z, and 1 angle, theta, or rectangular coordinates, which has 3 distances, x, y, and z. So to develop a relationship between rho, theta, and phi, and x, y, and z, we want to look at this triangle here inside of our 3-dimensional space. This triangle is actually a right triangle. The hypotenuse of this right triangle is rho. The height of the triangle is z, and the base of this triangle is r, because that's the r in the xy plane, just like in polar coordinates. So now we need to identify one of the other angles of this triangle. If we go back to the 3-dimensional picture, we can see that we have this vertical line z, which is parallel to the z-axis. The distance rho creates a transversal cutting through the parallel lines. So if this is angle phi, this angle up here is also angle phi by alternate interior angles. So from that, we can develop relationships using basic SOHCAHTOA trigonometry. For example, if we look at r and rho, r over rho is sine of phi, because r is opposite and rho is a hypotenuse. Opposite over hypotenuse is sine. So that means r equals rho sine phi. Let's take a look at all of this where I have a little bit more space. Given that we know from polar and cylindrical coordinates that x equals r cosine theta, now, since r equals rho sine phi, x equals rho sine phi cosine theta. This is now our conversion for spherical coordinates. Likewise, for y, we have r sine theta. So in spherical coordinates, this becomes rho sine phi sine theta. So how do we get the relationship for z? Well, if we look back at the triangle, we can see that z is adjacent to angle phi. Adjacent over hypotenuse rho would then be cosine phi. Therefore, z equals rho cosine phi. And we have our relationships for spherical coordinates. Other relationships to consider go in the opposite direction. So let's say we look at the triangle in terms of the Pythagorean theorem. We can see that rho squared equals r squared plus z squared. However, we know that r squared is x squared plus y squared. So this gives us the relationship that rho squared equals x squared plus y squared plus z squared. Or we can write that rho is the square root of x squared plus y squared plus z squared, because we usually restrict rho to be for just positive values. Theta is the same theta that we're used to in cylindrical coordinates. So the relationships with x and y are the same. Theta would be equal to arctangent of y over x. For phi, we're going to use the relationship that z equals rho cosine phi. So that means phi equals arc cosine of z over rho. But if we only want to see x, y's, and z's, that's arc cosine of z over the square root of x squared plus y squared plus z squared. These relationships are all listed, out here. So let's take a look at the simple spherical surfaces. So let's say we have rho equal to a constant. If rho is equal to a constant, that just gives us a sphere, because we have a fixed radius, c in this case, but theta is allowed to take on all possible values, and phi is allowed to take on all possible values. Note that rho is restricted to values that are non-negative. Phi is restricted to values between 0 and pi. We do not need phi to go all the way to 2 pi, because theta will go from 0 to 2 pi. So to see why we only need phi to go to pi, we can have a fixed value of rho, and it's a little hard to see up here. But if we let phi go from 0 to pi, that creates this half circle. Now theta, going from 0 to 2 pi, goes around and completes the entire sphere. We don't need both of them to go to 2 pi, because if they did, it would double up on itself. So again, for a fixed rho, we let phi go from 0 to pi, 180 degrees, then theta goes and takes care of all of the rest, 0 to 2 pi. So with this in mind, consider what happens if we have theta equal to a constant. So we have some fixed angle theta, but now we allow rho to take on all possible values and phi to take on all possible values. So when we do this, we create, you can imagine, a half circle that's infinitely big. This just creates a half plane, kind of just like it did in rectangular coordinates. But now we think of the plane as an infinite half circle rather than a half of a rectangle. Because we don't allow rho to be negative, we get only one side of the plane. Also, because phi only goes to pi, it stops at 180 degrees. What if phi is a constant? If phi is a constant, that gives us a constant angle coming off of the z-axis. But now, what variables are free? We have rho that can take on any length, but we also have theta, which indicates that we could take this and spin it around. This gives us one nap of a cone, a circular cone, going up in the z direction. So imagine taking this edge here and spinning it around the z-axis. Perhaps I could do this in an animation as well. Here, when we have a fixed angle phi, so this is the z-axis here. Sorry, none of these axes are labeled. I didn't take the time to do that. But here's angle phi coming down, and then we have rho taking on all possible values, and now theta comes around and takes all possible values. Then that produces a cone, or the upper nap of a cone. If phi is greater than pi over 2, so let's make 3 pi over 4 here. Now rho is down in this direction, and then when theta goes around, it makes the bottom part of the cone. So we can still get an entire cone, but we would have to have two separate values of phi to do that. Now let's take a look at what happens if we want to convert an equation to spherical coordinates. So here I have 4 times a quantity, x squared plus y squared equals z squared. So let's substitute in our conversions. X equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. If we substitute that in, we get 4 times the quantity, rho squared sine squared phi cosine squared theta, plus rho squared sine squared phi sine squared theta equals rho squared cosine squared phi. Of course, now we can factor out this rho squared sine squared phi. So this becomes 4 rho squared sine squared phi times the quantity cosine squared theta plus sine squared theta equals rho squared cosine squared phi. And this is nice because it cancels out to be 1, and we have 4 rho squared sine squared phi equals rho squared cosine squared phi. As long as we don't allow rho to be 0, we can cancel out the rho squareds. I'm going to rewrite this as sine squared phi over cosine squared phi equals 1/4. And the reason I did that, as you may notice, is this now is tangent squared phi equals 1/4. So tangent phi equals plus or minus 1/2, or phi equals arctangent of plus or minus 1/2. Now take a look at this answer for a moment. Don't worry about the plus or minus. I know that can make you nervous, but just ignore that for right now. What we have here is a constant value. This is phi equal to a constant. And as we just talked about, if phi equals a constant, what we have is a cone. In fact, the plus or minus gives us the entire cone, because one angle is going to be in this quadrant, and then the second angle is in this quadrant. And if we take that and spin it around for all possible values of theta, what we get is our circular cone along the z-axis. In fact, if you go back to the original problem, we have 4x squared plus 4y squared minus z squared equals 0. Just like what we saw with the cylindrical problem, which became 4r squared equals z squared, or z equals plus or minus 2r. In all of these cases, we had the circular cone. The shape did not change, but the equations did based on the coordinate system. Down below here is a chart for completing all of the coordinate conversions. I was not planning on doing this with you in class, but it's a good exercise for you to try on your own.